Here we continue our discussion on ideal flow, and we are leaving for a second the realm of the 2D planar geometry that we've been discussing so far to look at ideal flows which are three-dimensional, so not in the plane, but three-dimensional and axisymmetric. So really, they are not fully three-dimensional because they are axisymmetric, but at least they are not two-dimensional planar. And this is going to be useful once we look at the flow around flows which are not in the two-plane, but for instance the flow around a sphere, because in that case you have to imagine the sphere is no longer 2D axisymmetric, and therefore you have flow going in this direction, but also flow being deviated to the side. So flow around a sphere, or earlier in history, it was used to model the flow around zeppelins. Okay, and before we discuss that, we need to discuss new coordinate systems, and that's for this whole section. Conceptually, there's no difference compared to what we did before, except that you have to be comfortable with the coordinate systems. And so we'll start with so there are two coordinate systems. Everything is rigorously the same, but for certain geometries, it's easier to use a cylindrical coordinate system. And for certain other geometries, it's easier to use a spherical coordinate system. And when you're looking at flows which are axisymmetric, oftentimes we'll look at external flows. So in 2D planar flows, we looked at the flow around the cylinder. Here we're looking at the flow around the sphere. And we're assuming that the flow field here is coming along the axis of axisymmetry. And that means that the z-axis, which you usually have standing in this direction, we now have lying flat. Okay, but that doesn't change anything. The axisymmetry here is along the z-axis, whether we're looking at spherical coordinates or whether we're looking at cylindrical coordinates. So we'll start with the cylindrical coordinates, because this is the one which is the easiest. So let's say that we have a point somewhere. Here is our point. Vector position is x, and we don't want to have the position in x, y, z. What we want is the position in cylindrical coordinate, which is r, theta, and z. And what this corresponds to is, so if you project this point onto the xy plane, maybe this point here is located there, then z is the height, the position of the point, of this point here, its position along the z-axis, so that would be z. And once you've projected it on the xy plane, then the rest are just the polar coordinates. So if you look at theta, that would be this angle, and r, that would be the distance between the origin and the projection of the point. Okay, those are cylindrical coordinates. If you're looking at spherical coordinates, then it is not exactly the same. So if you have a point here, that's just for notation, the point is represented by, I'm going to still use the letter R, but sometimes in books you will see either rho or a capital R. I'm just going to use R because that's what I'm used to, the azimuthal angle and the polar angle. And so the way you have to think about this is, so think about a line which is going to go from the origin of your coordinate system to, so you can think as r as the distance between the point and the origin. And if you want to see what the two others are angles. So first what you do is you project, again, the point on the xy plane. And the angle between the x-axis and the projection of the point onto the xy plane is the angle phi. That is called the azimuthal angle. And the angle between the vector z and the line between the origin of your coordinate system and your point, this here is your polar angle theta. So of course in this direction it's a bit less similar, but this is very similar to what you may have seen before. So of course the fact that z is not in the usual direction is a bit confusing, but if you think about how this usually looks like. Let me just put this little cartoon here. Right, so this looks like that. Sorry. Right, so r is the distance between, this is your point, this is your coordinate system, x, y, z. R is the distance between your point and the origin. Once you've projected r on the xy plane, the angle between x and the vector between the origin and the projection is the azimuthal angle. And this here, the angle between z and your radial vector here is your polar angle. So theta is your polar angle and phi is your azimuthal angle. Okay, so with this coordinate system, now everything is the same as before. So what we'll do is we can define a potential, and the velocity field is going to be, if the flow is an ideal flow, so if you have an irrotational incompressible flow, we can define a potential, and we can define a stream function. All right, so let's look at those potentials. And now the potential, remember, all the formulas we have to take either in cylindrical coordinates or in spherical coordinates. I'm going to remind you just real quick what these are. So for the potential flow, how do we get to the velocity? Well, the velocity field u derives from a potential. Therefore, we can write that the vector u is equal to the gradient of a potential function. And of course, we have to take the gradient now in cylindrical coordinates. So we have three components. We have the components in the r direction, the component in the theta direction, and the component in the z direction. And the component in the theta direction here is equal to 0. And this is because we have axis symmetry. So the component in the r direction is simply d phi dr. And the component in the z direction is simply d phi dz. That is for the potential. Now let's look at the stream function. We can also define a stream function, and what we find is that the radial component of the velocity is equal to minus 1 divided by r d psi dz, where psi is the stream function, and the z component of the velocity, this one is going to be equal, if we know psi, the stream function, equal to 1 divided by r d psi dr. So this is the equivalent. If you go back to the stream function, we had defined it in Cartesian coordinates, but you can also define the stream function in cylindrical or in polar coordinates. Okay, this is for cylindrical coordinates. Now moving on to spherical coordinates. Again, the velocity field derives from a potential. So it will have, in that case, three components. The components in the r direction is going to be d phi dr, where phi is the potential. The component in the azimuthal direction is 0. This is the component in this direction here. And it will be equal to 0 because we have axisymmetry. And finally, the component in the theta direction is going to be equal to 1 divided by r d phi d theta. Okay, all of these formulas just put in the formula sheet. You don't have to know them by heart. You know these for Cartesian coordinate system. You have to know them, but for cylindrical and polar coordinates, you do not. Now let's finishing this quickly. There's the equivalent formulas for the stream function in spherical coordinates, where u r, the velocity in the radial direction, is equal to 1 divided by r squared sine theta, where theta is the polar angle, times d psi d theta, and u theta is equal to minus 1 divided by r sine theta, d psi dr. Okay, so with all of that, you know how to compute the velocity field, giving a potential or a streamline, and then it's exactly the same as what we had for 2D planar flows. We have building blocks, and we have exactly the same building blocks as what we have in 2D planar flows, except for one, and that is the irrotational vortex. The irrotational vortex has no equivalent for 3D irrotational flow. Remember that vortices, we talk about vortex filaments, and if you have a ball like this, the moment you start having some sort of circulation, then you lose the axisymmetry. and therefore we have no equivalent of the irrotational vortex for 3D axisymmetric flow. But other than this, it is very similar, and I'm not going to write all of that because this is going to be a little bit long. I refer you to your book. In page 326, you have all of the formulas that you need. So I just put them here as a reference. These are the formulas. So you have the uniform flow. And here, as we discussed, it's a uniform flow in the z direction. You have the point source of strength Q, or it could be a point sink if Q was negative. And you have a dipole, right? And we have a dipole along the z direction here. Phi is the potential. Psi is the stream function. And on the left-hand side, all of this here is for cylindrical coordinates. And on the right-hand side, we have the same. Phi represents the potential and psi the stream function, but this time in spherical coordinate. Remember here that theta is the polar angle, so it's the angle from the z-axis. It's not the same as in cylindrical, or it's not the same theta as in cylindrical or in polar coordinate system. Note here that in Kundu, they follow the same notation as I do for the spherical coordinates, but I was wrong. Actually, it's in the cylindrical coordinate. They use a capital R, where I used a small r. So in Kundu, this small r is a capital R in Kundu. And then what you can do after that is do the same as what we did in 2D planar flows. So we can build flows by adding the potential of building blocks. So we could take a uniform flow on top of a point source or on top of a doublet, and the flow, and then this still represents an ideal flow. And so if you added the potentials, if you wanted to know what the velocity field was, then you would take the gradient. If you add the stream functions and you want to know what the velocity is, then you use these formulas here. They're exactly equivalent.